Hello everyone, so we will be solving February-March 2022 question paper 12 today. So question 1 says, what could not be a measurement of a physical quantity? A 10 Kelvin, B 11 joules per Newton per meter, C 17 Pascal meter cube per Newton, or D 25 terameters. Now if it's a physical quantity, it needs to have a magnitude and a unit. 10 Kelvin, this looks like a physical quantity. 11 joules per Newton per meter. Now let's see. Joules per Newton per meter. Joules, if I simplify joules, I can write joules because joules is the unit for energy. It's force times distance. I can write it as Newton meter. So Newton meter upon Newton meter. This cancels out. So basically these units cancel out. So B could not be a physical quantity. If you look at C, C says 17 pascals meter cube per Newton. So let's write it as 17 pascals meter cube per Newton. Pascals is the unit for pressure. Pressure is force per unit area. So Pascal here can be written as Newton per meter squared. So when I replace this Pascal, what do I get? Newton per meter squared multiplied by meter cube over Newton. The Newtons cancel out, the meter square cancels out with the meter square, but we're still left with 1 meter in the numerator. So this unit could be simplified to meter. This here is terameter, it's a unit. So the only option which has no unit is B, hence this could not be. There's a chance that this is not a physical quantity. Question 2 says a computer memory stick is labeled as having a storage capacity of 128 GB, where G is gigabyte. The letter B stands for byte, which is the unit. What is the equivalent storage capacity? 128 giga represents 10 to the power 9 byte. Because all the values here are in standard form, 1.28. If I convert this into 1.28, this becomes 10 to the power 11 byte. That is option B. Question 3 says a man of mass 75.2 kilogram uses a set of weighing scales to measure his mass 3 times. He obtains the following readings. Which statement describes the precision and accuracy of the weighing scale? So what is precision? Precision is basically the readings being close to each other. That's precise. Accuracy basically is how close the readings are to the true value. The true value in this case is 75.2 kilograms. Now all the readings here are precise to plus minus 0.1 kilogram. So it's 80.1, 80.2, 80.2. Even if we take out the average of the 3 values, the average of the 3 values comes out to be 80.133. So this here is the average value, 80.133. So the 3 values are precise to plus minus 0.1 kilograms. So they are precise to plus minus 0.1 kilograms. So it could be either option C or option D. If you look at the accuracy, is the average value accurate to plus minus 0.1 kilogram? It's not. The true value is 75.2. The average value is 80.133. So it's not precise. It's not accurate to 0.1 kilogram. Hence option D. Question 4 says, which statement about scalar and vector quantities is correct? A scalar quantity has a direction, but not magnitude. No, that's not the case. A scalar quantity has a magnitude, but not a direction. That is correct. A vector quantity has a direction, but not magnitude. No, a vector quantity has both a direction and a magnitude. Option D says a vector quantity has a magnitude, but not direction. No, it has both. A scalar quantity only has a magnitude, but no direction. A vector quantity has both a magnitude and a direction. Question 5 says, how can the acceleration of an object be determined? A, from the area under a displacement time graph. The area under a displacement time graph does not give us acceleration. It does not represent anything, in fact. From the area under a velocity time graph. The area under a velocity time graph represents displacement. Option C says from the gradient of a displacement time graph. The gradient of a displacement time graph gives us velocity. D says from the gradient of a velocity time graph. Yes, the gradient of a velocity time graph represents acceleration. Question 6 says a sprinter takes a time of 11 seconds to run a 100-meter race. She first accelerates uniformly from rest, reaching a speed of 10 meters per second. She then runs at a constant speed of 10 meters per second until the finish line. What is the uniform acceleration of the sprinter for the first part of the race? So for this, we need a graph. That's the easier way to do this. So I've drawn a graph here. It's a speed time graph. And what the graph shows is that the sprinter accelerates uniformly to a speed of 10 meters per second in a time t1, which is an unknown, and then continues with the same speed, 10 meters per second. The total time elapsed is 11 seconds. And in this total time, the sprinter basically covers 100 meters. So this total area under the graph is 100 meters. So because the shape is a trapezium. Now, before we move on to that, how do we find out the acceleration? We need change in speed or change in velocity upon time. We don't have the time. If we could somehow get the value of t1, we could find out the acceleration. So the area under the graph represents distance, and the total distance is 100 meters, and the shape here is a trapezium. The formula for a trapezium is half into height into sum of parallel sides, p1 plus p2. And this is equals to 100. So half times the height of this trapezium, which is 10, plus one of the parallel sides is this, which is basically 11 minus t1. And the second parallel side is this entire thing, 11 seconds plus 11 is equals to 100. Solving for t, what we get is t1 is equals to 2 seconds. So we've got this value here for t1. To find out the acceleration, we'll say change in velocity upon time. The sprinter went from 0 to 10. So the change in velocity is 10 upon the time, that is 2 seconds. The acceleration comes out to be 5 meters per second, hence option D. Question 7 says a single horizontal force F is applied to a block X which is in contact with a separate block Y as shown. The blocks remain in contact as they accelerate along a horizontal frictionless surface. Air resistance is negligible. X has a greater mass than Y. Which statement is correct? The acceleration of X is equal to force F divided by the mass of X. No. So let's try to understand what happens to the forces. Once we apply a force F on X, F applies a force on Y. Let's call this force Fxy, the force that X applies on Y. In return, Y applies an equal but opposite force on X. Let's call this Fyx. So now if we talk about the acceleration of X, we need to consider the forces acting on X. There are two forces, F that we are applying and this Fyx that Y applies on X. So the difference between the two divided by the mass of X would give us the acceleration. Hence this is incorrect. You cannot just use F to get the acceleration. You can use F to get the combined acceleration of X and Y, but then you'll have to divide it by the mass of X and Y. Part B says the force that X exerts on Y is equal to F. So the force that X exerts on Y cannot be equal to F. Why? Because the two blocks have the same acceleration. So if this F, the force on Y is equal to F, the acceleration of Y would be greater. So that's incorrect. C says the force that X exerts on Y is less than F. This is correct. It will be less than X. D says the force that X exerts on Y is less than the force that Y exerts on X. This goes against Newton's third law. An action has equal and opposite reaction. So this force should be equal and opposite to the other force. So the correct answer is C. Question 8 says a car of mass 750 kg has a horizontal driving force of 2 kilonewtons acting on it. It has a forward horizontal acceleration of 2 meters per second squared. What is the resistive force? The formula is resultant force is equals to mass times acceleration. The resultant force is the driving force, which is 2000 newtons, minus the resistive force, let's call this Fr, is equals to the mass, that is 750, times the acceleration, which is 2. Solving for Fr would give us 2000 minus 1500, which is equals to 500 newtons, or 0.5 kilo newtons. So the answer is A. Question 9 says, an object falls freely from rest in a vacuum. The graph shows the variation with time t of the velocity v of the object. Which graph using the same scales represents the object falling in air? So this is the graph of the object falling in a vacuum in the absence of air. There's a constant acceleration. The gradient of the graph is constant. When the same object falls in the presence of air, the acceleration decreases, which means that the gradient would reduce. Most students know the general shape of the graph, and if you know that, you'll be able to shortlist B and C. So it could either be B or C. A is incorrect because the gradient is constant. It does not decrease, which means the acceleration is not decreasing, which is not possible for an object falling in air. D is also incorrect because the gradient is increasing, which means that the acceleration is increasing despite having air resistance and opposing force. So D is incorrect. Now the question is, can it be B or C? Now, this here is in bold. So this here is the key statement, using the same scales. What we need to understand is, for the object falling in the presence of air, at any given point in time, the velocity cannot be greater than the same object's velocity falling in vacuum. So now let's trace this graph. This is the graph for B. This is the velocity time graph. If I move this graph from B to our original graph, what we notice is that at all these points, the velocity of the graph of the object falling in the presence of air is greater than the velocity of the object that is falling in vacuum. So this is not possible. Hence, B cannot be the correct answer. But on the other hand, if you look at C, C is always below. C will always be below. If you could trace it here and copy it over here, you'd see that C is always below the graph of the object falling in vacuum. So C is the correct answer. Question 10 says, a rock of mass 2m traveling in a deep space at velocity v explodes into two parts of equal masses, one of which is then stationary. What is the kinetic energy of the moving part after the explosion? So let's say we've got this rock, mass 2m, traveling to the right with velocity v. And when it explodes, I know one thing for sure is that they have equal masses, because that's stated in the question. Number two, that the mass that is moving, let's say the mass on the right is moving, the mass that is moving would move with the velocity of 2v. The other mass is stationary. And why is it that this would move with the velocity of 2v? Because momentum needs to be conserved. So the initial momentum, which is 2mv, should be equal to the final momentum, that is also 2mv. So now we have the mass and the velocity of the moving rock. So the kinetic energy is half times mass times velocity, which is 2v squared. And this gives us m4v squared over 2, which is equal to 2mv squared. That is option D. Question 11 says, a horizontal metal bar PQ of length 50 centimeters hinged at NP. The diagram shows the metal bar viewed from above. Two forces of 60 newtons and 5 newton are in the horizontal plane and act on end Q as shown. What is the resultant moment about P due to the two forces? Now, to calculate moment, we need the force and the perpendicular distance from the pivot to the line of action of the force. So for this 5 newton force, we know that this is 50 centimeters. This is the perpendicular distance, or 0.5 meters. For the 16 newtons, we can either calculate this perpendicular distance, or we can resolve the 16 newton force into two components so that one of the components is perpendicular. This component here is the perpendicular component, which is 16 sine 30. The other component is the component 16 cos 30. Now the 16 cos 30 component passes through the pivot, and hence its moment is 0. 16 sine 30 is equals to 8. Now I can either multiply 16 sine 30 or 8 with the distance and calculate this moment, which would basically be our anti-clockwise moment, and multiply 5 by 50 and calculate the clockwise moment and then subtract the two. Or what I can also do is, because the two forces act from the same point and the distance from the pivot is same, I can also subtract it first. So the net force is 8 minus 5, which is equals to 3 newtons in this direction. So the moment will be 3 times 0.5 meters, which is equals to 1.5 Newton meter. Hence option A. Question 12 says, a cube WXCY has sides of length 2 centimeters and mass 24 grams. The cube rests on a meter rule of negligible mass. The geometrical center of the cube is vertically above the 70 centimeter mark on the scale of the rule. The cube has a non-uniform density. So the center of gravity is not at its geometrical center. So the center of gravity could be anywhere inside the cube depending on the distribution of its density. The rule rests on a pivot at the 50 centimeter mark. A mass of 23.4 grams is placed vertically above the 30 centimeter mark. The rule is horizontal and in equilibrium. What can be determined about the position of the center of gravity of the cube? So center of gravity is the point through which the weight of the cube acts. So let's calculate the moment and let's find out a point about which the force acts. So I know this here is my anti-clockwise moment, and the cube would produce a clockwise moment. And since they're in equilibrium, the anti-clockwise moment will be equal to the clockwise moment. Now, ideally, I should convert this mass into kilograms, multiply it by the gravitational field strength G, and then multiply that by distance, that too converted in meters, to get the answer in SI unit. But since we've got the same conditions on both sides, they will cancel out. So I don't need to do that conversion. I can simply multiply mass, 23.4, multiplied by the distance. This distance is 20 centimeters. Let's multiply this by 20. Is equals to the other mass, which is 24, multiplied by x, because I don't know the exact position. I don't know the exact position where the weight acts from. So let's call this x. X could be any distance. The value of x that we get is 19.5 centimeter. What does that mean? This basically means that our weight acts from a distance of 19.5 centimeters from the pivot. So at a position of 69.5 centimeters. That is for sure. That is the only reason that it is balanced. So what can be determined about the position of the center of gravity of the cube? It must be somewhere along a horizontal line that is 0.5 centimeter from line WX. So can we say for sure that the center of gravity acts 0.5 centimeter from WX? We don't know. It could be or it could not be the case. If it acts over here, it must be somewhere along a horizontal line that is 0.5 centimeter from line YZ. Does it act in this line? It could be. It could act over here, exact position, but we don't know. We can't say that for sure. It must be somewhere along a vertical line that is 0.5 centimeter from WY. Yes, that is what we calculated. I can say for sure that it acts from one of these points on the line. That is 0.5 centimeters from this side WY at 69.5. So C here is our correct answer. Question 13 says, a rigid sphere is held at rest on the seabed. When the sphere is released, it rises to the surface of the sea. The seawater has a uniform density. Which statement about the sphere from its release until it reaches the surface is correct? The sphere always moves with a constant acceleration. Nope. The sphere will not move with a constant acceleration. For the sphere, the forces that act on it is the weight of the sphere, there's upthrust, U, and there will be a frictional force or drag force in the opposite direction to its motion. So that acts downwards. But the drag force increases as the speed increases. Hence, that would change the net force and the acceleration. So this is incorrect. The sphere always moves with a constant velocity? No. The sphere may reach some terminal velocity. When the net force balance out, there is no net force. When the upward force is equal to the downward force, but not always with constant velocity. The upthrust on the sphere always decreases. Upthrust depends on the pressure difference. And the pressure difference depends on rho, g, and h. The seawater has uniform density, as stated in the question. G is constant, and so is the height or this height of the sphere. So the upthrust on the sphere decreases? No, it does not. So irrespective of the depth of this, the depth of water the sphere is in, the upthrust stays constant. The upthrust on the sphere is always constant, yes. And when I said upthrust earlier, I know this is basically the formula for pressure difference, and that is what we use to calculate upthrust. We multiply that by the cross-sectional area to get the upthrust. So upthrust is constant. Question number 14 says, what is a unit for density? Newtons per meter cube. Is that the unit for density? No, it's not. You can simplify this. Newtons is kilograms meters per second squared upon meter cube. This cancels out. You get 2 over here. Kilogram per meter squared per second squared. That is not the unit for density. Grams per millimeters? No. Kilograms per centimeter squared? No. Microgram per millimeter cube? Yes, density is mass over volume. Mass measured in micrograms, volume measured in millimeter cube. So D here is the correct answer. Question 15 says the total energy input E in a process is partly transferred to useful energy output U and partly transferred to energy that is wasted. What is the efficiency of the process? Efficiency by definition is the percentage of the useful output to the input energy. So useful output over the total input energy multiplied by 100 gives us efficiency, and that is option A. So question number 60, this is a repeat question from 2014, so you may have seen this earlier. An escalator is 60 meters long and lifts passengers through a vertical height of 30 meters as shown. To drive the escalator against the forces of friction when there are no passengers requires a power of 2 kilowatts. The escalator is used by passengers of average mass 60 kilograms and the power to overcome friction remains constant. How much is required to drive the escalator when it is carrying 20 passengers and is traveling at 0.75 meters per second? So we already know the power needed to move against the forces of friction when there are no passengers. We just need to calculate the power needed to move the passengers 60 meters or 30 meters vertically when there are 20 passengers each having a mass of 60 kilograms. So the weight of the passenger is 60 multiplied by 9.81 multiplied by 20 would give you the total weight. Because there are 20 passengers, we would like to calculate the total weight, which is equals to 11,772 newtons. Now the weight acts downwards, but the force applied by the escalator is in this direction. So we need to calculate the component of weight. So the weight that is acting downwards, we need to calculate the component of weight in this direction. If we could calculate this angle theta, we know that with respect to this angle, this component would be W sine theta. How do we calculate theta? We've got a triangle here with the hypotenuse being 60. This is theta. This is 30. So sine theta is opposite over hypotenuse or perpendicular over hypotenuse. Sine theta is equals to 0.5. So the component of weight against which the force would be applied by the escalator is W sine theta. Now to calculate power, power is force into velocity. Force being 11,772 sine theta, which is equal to half. You already know the value for sine theta, so half into this velocity, which is 0.75. This gives us the power as 4.4 kilowatts. Now this is the power needed to move these 20 passengers. But we need some power to overcome friction even when there are no passengers, and that power is constant. So we got to add the two powers, 4.4 plus this 2 kilowatts, which is equal to 6.4 kilowatts. Hence, B is the correct answer. Question number 17 says, a rock of mass 40 kilograms is released from rest from a height of 20 meters from above the surface of a planet. The rock has a kinetic energy of 32 kilojoules. When it hits the surface of the planet does not have an atmosphere. What is the weight of the rock on the surface of the planet? So what's happening here is that for this rock that drops from a height from rest, its gravitational potential energy gets converted into kinetic energy. So I know that mgh is equals to kinetic energy, which is 32 kilojoules EK. They're asking us for the weight of the rock, which is basically mg. So to find out the weight, or mg, I know that will be equal to kinetic energy divided by the height. The kinetic energy is 32 kilojoules divided by the height, that is 20 meters. 32 over 20 is 1.6 kilo newtons. So the answer is C. Question 18 says, a metal wire is stretched. The wire obeys Hooke's law. Which quantity has a value that does not change? So extension. When the wire is stretched, the extension will change. Strain. Strain is extension over original length. So even though the original length is a constant, but because the extension changes, the strain changes too. Stress, which is force over area. The force will change because the wire stretches because there is an increasing force. So the stress changes too. Young modulus. Young modulus does not change. Young modulus is a material dependent property. So Young modulus of a particular material is a constant. So for copper, irrespective of the dimensions of copper, irrespective of the size of that piece of copper, the Young modulus stays constant. Question 19 says, an object is stretched until it reaches the elastic limit. Which statement must describe the stress on the object when it is at the elastic limit? So elastic limit is the point. It's the maximum value of force beyond which the object experiences plastic deformation, or it deforms permanently even when the force is removed. So option A says it is the maximum stress for which the object obeys Hooke's law. No, that is not the case. That point is known as the limit of proportionality and not the elastic limit. It is the maximum stress that can be applied to the object before it has elastic deformation. No, beyond this point it has plastic deformation. So this is incorrect. It is the maximum stress that can be applied to the object before it has plastic deformation. That is correct. C. It is the maximum stress that the object can withstand before it breaks. No, that is known as the breaking point. That is the maximum of stress that the object can withstand. Question 20 says, which statement about progressive waves is correct? They are always transverse waves. Now, we can have longitudinal waves that are progressive. Sound waves, longitudinal and progressive. They can exist in solids, but not in liquids. Progressive waves can exist in both solids and liquids. they decrease in frequency as their speed increases. That is incorrect too. They transfer energy away from their source. This is correct. That is what happens in a progressive wave. Energy moves away, hence the name progressive. So D is the correct answer.